Welcome to Approximations. We are taking a little bit of a step back from integration for a hair bit, and we are talking about how do we approximate values based on other values about a function, or maybe we don't even know the function. So you have to remember that everything in the world of calculus is based on the idea, like it was all discovered. Nobody just woke up one day and knew, hey, this is calculus. No, they were trying to find stuff out about different points and different patterns that they were seeing, and they were trying to make justifications on why the patterns were behaving the way they were, and if we know this pattern, can I make an approximation for what's going to happen next? Okay, so that's kind of the lead in to what we're doing today, but we're going to start with something real simple, which is called linear approximation. So I have this graph shown. This is actually g prime. And what I know, so I don't actually know the function g, I only know g prime. G prime looks like what you're seeing here, and I know that g of 2 is -3. So I have my derivative, I have the function, I have the curve for my derivative, and I have my actual y value at a given point on my function, but that's all that I know. Okay, so part A is asking me to use a linear approximation to approximate g of 2.1. Well, I don't actually know what the function is, because if I did, I would just plug in 2.1 into my function. It would make life a lot easier, but I don't know that. So instead, I'm going to find the line at 2, because that's what I know basically so far. I'm going to find the line at 2 and then use that to make a pretty good approximation for 2.1. Okay, so again, I don't want to draw the line here because this actually isn't my function. This is my derivative, okay? So, and again, if it helps, you can always label that as g prime. It's probably helpful because I guarantee you some of you guys read that as, oh, this is a function g. G of 2.1 is just boop, boop, right there. No, no, no. This is g prime, okay? Well, g prime helps me determine the slope, okay? And so in order to find a linear approximation, I essentially need y minus y1 equals m x minus x1, okay? Because I need to find a line, all right? So, and anytime we need a line, you need two things. You need a point, x1, y1, or x1, y1, and you need a slope. Well, I have the point, g of 2 is -3, so the point that I have is 2, -3, and then my slope at 2, okay, because remember we just needed this, actually I'll call that g prime of 2, so that way we're not confused here. So g prime of 2 I just look at the curve that I have. G prime of 2 is 3. So my tangent line at 2, -3 is going to be y minus -3 equals 3 times x minus 2. Okay, this is the equation for the tangent line at 2 on my original curve. Okay, at the point 2, -3. Well, I want to know what's happening at the point 2.1. Well, what I would do is I just graph I could graph this line, or I could say, hey, you know what? I know what my slope is doing at 2. At 2, my slope is 3. So I'm just going to make the rough prediction that my slope is going to continue in roughly the same pattern. So I can just go ahead and plug in 2.1 into my tangent line at the previous point, and then just kind of hope for the best here. So this is y plus 3 is equal to 3 times, now again, I'm going to approximate it at 2.1, so 2.1 minus 2, all right, and then I'm going to end up with y, if I simplify, 3 times, well actually, sorry, 2.1 minus 2 is just 0.1, times 3 is 0.3, right, and then subtract the 3, you get -2.7, so roughly g of 2.1 is approximately -2.7. I don't know if that's exactly right. I also don't care if it's exactly right, because we're trying to just find an approximation, okay? I'm approximating what I think could be the answer based on what's happening at a point that's pretty close to it, and because I have the slope at that point that's pretty close. So then part B is asking me, is the approximation in part A an over or under approximation? Justify. Well, let's see here. So if I'm just drawing my function here. My tangent line was, it went through the point 2, -3, so 1, 2, 1, 2, 3. It had a slope of 3, so 1, 2, so looks like this, okay? This is my tangent line, roughly, okay? I have no idea what the function looks like. What I do know is my derivative is doing something here. My derivative is increasing here. Well, if my derivative g prime is increasing, what does that tell me about g, like double prime? If g prime is increasing, that means g double prime is positive. Well, I know if g double prime is positive, well, what does that tell me about g, my original function? That tells me my original function is concave up. So if all I know, based on my graph of my derivative, okay, if all I know is that the derivative is increasing, then I know that my second derivative is positive, which means my original function is concave up. So then wherever my tangent line falls, if my function is concave up, at least at 2, I don't know what it's doing everywhere else, just at 2, my function is concave up. Again, I don't actually know what the function looks like. I'm just drawing something concave up right here. What do you notice about where the tangent line is in relation to the curve? The tangent line, I mean, obviously it touches it at the point 2, -3, but as you get further away, the tangent line is below the curve itself because it's concave up. So then the answer to part B is the approximation in part A, an over or under approximation. This would be an under approximation because G is concave up at 2, -3. Okay? So because it's concave up, the tangent line will fall below. Here, let me go ahead and add that in there. So under approximation, because G is concave up at 2, -3, and tangent line falls below. So basically, as I get further away from my point that I know, it's going to be further and further off, like my actual approximation is going to be further away from the true value because my function is concave up. It'll be below it. So any type of tangent, any type of linear approximation on a function that's concave up is going to be an under approximation. Well, what if my derivative looked like this instead? Now what do you notice about your derivative? Well, g prime of 2 is still 3, but now your derivative is decreasing as opposed to increasing. Okay, so then use a linear approximation to approximate g of 2.1. Well, that's going to be exactly the same because my slope at 2 is still positive 3, so my tangent line is going to be exactly the same. So g of 2.1 is still approximately -2.7. Did I write the negative on the last slide? I meant to, and I feel like I didn't. Nope, I sure did. Okay, good. It's still -2.7. Okay, but now let's think about this. Is the approximation in part A an over or an under approximation? Well, now that my derivative is decreasing, that means g double prime is less than 0. Well, and if g double prime is less than 0, that means g is concave down. So if my function is concave down, my tangent line is going to go above, except at the one point except at the point of tangency, everything else is going to be above. So this is going to be an over approximation because g is concave down and tangent line falls above g. or above the actual curve. Okay, so in general here, what the idea behind whenever we do a linear approximation, if your function is concave up, tangent lines, whoa, that's terrible, hang on, tangent line approximation will always fall below the actual curve. And approximations will be under. Okay? If your function is concave down, it'll be the exact opposite. Basically, this is going to be the exact opposite. Tangent line approximations will always fall. You know what? I'm going to do my little cheat here. Nope, I don't want all that. I just want, I'm going to spend so much time trying to cheat the system here. And, we got it. Tangent line approximations will always fall above the curve, and approximations will be over approximations. Okay, if you need a quick visual, concave up, tangent line approximation. All of your approximations along this line are below the curve. Okay, so they are under approximations. If your function is concave down, tangent line approximations are all above the curve, so they are over approximations. Okay? Well, some guy, his name is Euler, but some guy named Euler was like, well, what happens as you get further and further away from the given x value? Well, as we've kind of already talked about, if this is my point of tangency, that's the only point that I know for certain what is happening on the actual function itself, that I know, like, hey, this is my x, this is my y. And I also know the slope at that point, hence I can draw the tangent line approximation. Okay? But as I get further and further away, as I make approximations for points along that line, further and further away from my original point, my approximations get further and further off. Okay? So some guy named Euler decided, well, hey, what if we do an approximation here, but then I recalculate my slope to where it's a little bit closer, and then I come up with a different line that might be a little bit closer. Okay, so I'm going to show you his process here in just a second. So this is the intro to what we call the Euler's method. Okay, I know you see this and you think, oh, his name is Euler. Nah. He's German. This is pronounced Euler. Okay, so this is a numerical approach to approximating the particular solution of a differential equation or a derivative, so we have a more accurate tangent line approximation. What? That's a lot of words. Let me show you in pictures. Okay? All right, so let's pretend for a second that this is the actual curve that I'm trying to approximate. I don't know what it is, but it's there. So what I mean by that is, let's say, kind of like what we started with earlier, I have a point. So I have a specific point that I know, x naught, y naught, okay? And I have an understanding of what the slope is at that point. I don't know what the function looks like, but I know what the slope is. So what I do is I create my tangent line, okay? And again, you have to remember that we're pretending like we don't know what this curve is. Okay, I'm showing you what it is to kind of let you know that that's where we're going, but we have to pretend that we don't know what it is. But we know the slope, and we know a point. Okay, well, with that, I can draw a tangent line. Okay, and then I can go however far away, h we'll call it, and then I can create a new point there. Okay, well, Euler is the guy that was like, hey, if I just keep going along that same line forever and ever, I'm going to get further and further away from my approximation here. And that's really not going to work. So what he decided to do was, if I already know what the slope is supposed to be like for my original function, I can recalculate my slope at this new spot that I have created, and then I'm going to get a tangent line that's not going to be exactly along the curve, but it's going to be a lot closer than if I had just stuck with the tangent line that I had before. Okay, and then depending on how many steps or iterations that I wanted to do, how many points I wanted to approximate, I could keep going. So let's say we just wanted it 2 points away. So then my new approximation, see how much closer that would be as opposed to if I had kept this going all the way down here. Okay, so he's the guy that basically discovered this idea. Okay, so we have this slope, but we're trying to use the slope to come up with the actual function itself, the actual curve that fits this slope. Okay, so this is the intro to Euler's formula. In order for you to have Euler's formula, you are always going to be given two things. You are always given a point, and our initial point, we always call it x naught, y naught, and then a slope. Okay, so you're always given a point and then a slope. Your slope can be written in a variety of different ways. Because remember, anytime we need to come up with a tangent line, you need two things, point and a slope. Okay, so got the point. Your slope, we could write it as dy dx equals something, or we'll call it f prime at x naught, y naught, or x in, y in at any given point. Actually, I'll go ahead and just say at any point. X in, y in. Okay, this represents slope at any point on the curve. Okay, all right, so let's go back to our tangent line. Okay, our tangent line, we always start out with point slope form, thinking back to algebra 1. Y minus y1 equals mx minus x1. Okay, this is algebra speak though. Okay, we've matured, we've grown up, now we need calculus speak. Okay, so I'm going to replace y1 and x1 with the initial point that I'm given. So y minus y naught is equal to, I'm going to replace m in just a second, so I'm going to have x minus x naught. Okay, so m, instead of just calling it m because that's what we did in, 8th grade, 9th grade, whatever grade you took algebra 1, I'm going to use one of these two things. The most common one is going to be this guy right here, f prime x in, y in. Okay, and specifically, well, I say x in, y in because I'm looking initially at x naught, y naught. I'm actually going to say that my slope here is going to be f prime x naught, y naught, and then x minus x naught. Okay, and this represents the slope at specifically x naught, y naught. So if it helps here, this is tangent line at x0, y0 with slope at x naught, y naught. Okay, when I use the n here, that's for any point, but specifically right now I want the slope just at the point x naught, y naught. Okay, now I'm going to use this to make my prediction for y1. Okay, so and anytime, I guess I should also say that you are also given the distance between x1 and x2, or x0 and x1. Okay, so we'll always tell you like, hey, I have, oh gosh, let me try to, earlier we had g of 2, right, was -3, and I was asking for g of 2.1. I will always tell you the distance between the points that I'm asking for. So here that distance is 0.1, or that's your h. Okay, so now I'm going to use this to make my approximation for y1. Okay, so y1 minus y naught is equal to f prime at x naught, y naught times x1 minus x naught. Okay, I'm going to give you what this point is, or at least tell you how far away it is from your original x value, so that way you can use that distance to predict what y1 is. Okay, so then now if I wanted to just solve for y1, well, y1 is going to be f prime x naught, y naught times x1 minus x naught plus your previous y naught. Okay? That is how you would approximate your next point. Now, let's say I already have x1, y1, and now I want to approximate y2. So to approximate y2, using the same pattern, I would use the slope at my previous point, so x1, y1, x2 minus x1 plus y1. Do you guys see the difference? This is to approximate x1, y1. Okay? This is to approximate x2, y2. I use the information from my previous point, both the slope and the point itself, to come up with my values for my next point. Okay? So in general, for Euler's method, do I have that? Nope, this is just an example page. So in general, I'm going to do a little modification here. Bear with me for just a second. It's thinking about it. There we go. In general, for Euler's formula, okay, you are going to have, I'm going to give you a starting position, okay? So my next x value is equal to my previous x value plus h. This is called the step, okay? Like, for example, 2 to 2.1, my step was 0.1, okay? I'm going to need to know what is y of n plus 1. Okay, y of n plus 1 is the slope at the previous point times that step in between. Now, I'm going to go back a page for a second. Come down here. Okay, x1 minus x naught. Okay, this is h. That's the distance between the 2 points. Okay, distance between the 2 points. So instead of saying xn minus xn plus 1, or vice versa, I'm just going to say h, okay, plus y of n. All right, I feel like maybe that's a little bit confusing. So if it helps, here, let me try this one more time. Okay, so a minute ago we did this as xn plus 1 minus xn plus yn, right? So then this guy right here is h. So yn plus 1 is equal to the slope times h, your step, plus your previous y value. Okay? So I'm going to go through one example here. Please, by all means, if you need more help with this, Prof. Rob Bob, Khan Academy, all that good stuff. Okay? All right, so use Euler's method to approximate the particular solution of the differential equation y prime is equal to x minus y passing through the point 0, 1. Use a step of 0.1. Okay, so again, whenever we're learning something new for the very first time, I always want you to write the formula out to make sure that you know exactly what you're doing. Okay? So we're trying to approximate the particular solution to this that passes through 0, 1 using a step of 0.1, okay? So let's approximate it to 2 places, or to 2 points, okay? So this right here, now notice it's written as y prime equals x minus y. Y prime is another way of saying dy dx, okay? So this is your slope at any point on y. I just don't know what y is. If I knew what y was, I wouldn't be doing any of this nonsense. I wouldn't be doing any of these approximations. I would just plug the numbers into the function itself, but I don't know them, so I have to do these approximations. Okay, so I am given x naught, y naught is equal to 0, 1. All right, I need x1, y1, and then I'm going to also use that to find x2, y2. I'm going to go ahead and show you both of those, okay? So then, remember for Euler's, I have x of n plus 1 is equal to x of n plus h, y of n plus 1 is equal to f prime at my previous point times h plus the y value at my previous point. Okay, so I have x naught, y naught. The first thing I'm going to go for is x1, y1. So x1 is going to be equal to x naught plus h. X naught was 0. H was 0.1. So that is 0.1. Y1 is going to be equal to my slope at x naught, y naught times h plus y naught. Well, my slope at x naught, y naught, well, I have to use this process right here, okay? My slope is where I plug in x minus y. So basically, no matter where I'm at on my curve, the relationship of my slope is always that it's the x value minus the y value. Always, okay? For this particular function. It will be different every time. So my x value was 0. My y value was 1. So then my slope at my previous point is 0 minus 1 because I've plugged in x minus y into y prime. H was 0.1 plus my previous y value, which was 1. Okay? So then I just clean this up a little bit here. Negative 1 times 0.1 is negative 0.1 times 1 is 0.9. So now x1, y1 is equal to 0.1, 0.9. Okay? X naught, y naught was 0, 1. x1, y1 is equal to 0.1, 0.9. I'm going to use that now to come up with x2, y2. Okay? Scroll down. x2 is equal to x1 plus h. So that's going to be 0.1 plus 0.1, so 0.2. y2 is equal to f prime at x1, y1 times h plus y1. So that's going to be, now instead of plugging in 0 minus 1 into x minus y, I'm going to plug in this point right here. So now I'll say x minus y is 0.1 minus 0.9 times h, which is 0.1, plus my previous y value is 0.9. I clean all that up. This is negative 0.8 times 0.01 and then plus 0.9. This works out to be 0.82. Okay, so now x2, y2 is equal to 0.2, 0.82. Now, I could keep doing this as many times as I wanted to. The more points that I have, the more accurate my approximation is for my overall curve, and also the closer the points are, the more accurate it is. Okay, so on this next page right here, if I had continued on with this, I would have approximated a lot more points here. So this is the black curve right here is my approximation, and the gray is the exact solution. Do you see how much closer that is as opposed to if I had started here and just done a tangent line here? That would have been my approximation, is my tangent line. But it's going to get so much further away from the actual value, or the actual curve, as opposed to doing the Euler's method where it gets closer and closer. Okay, so that's Euler's method. Basically, you're just doing the same thing over and over again, as many steps as they tell you to take. So if this was confusing to you, Prof. Rob Bob, Khan Academy, CalcChat, CalcView, go through all of those options and those resources. But basically, it's just a little bit of practice here at this point. So you are finding tangent lines, approximating a point, calculating a new slope, using that new point, and then doing another tangent line and another approximation. It's just repeated linear approximations over and over again. Okay? Yeah, so that's Euler's method and linear approximations. In your textbook, those are 3.7 and 5.1 if you are keeping track of that. And again, CalcChat, CalcView, Prof. Rob Bob, and Khan Academy.